Okay, I was asked to give some lectures on supersymmetric grand unification, and the lecture notes are already posted and some homework problems are posted. I should say good morning to everybody. The lectures, each lecture is sort of a different subject. So lecture 1, lecture 2, and lecture 3 will describe an evolution of supersymmetric grand unified theories. And what I mean by that is that lecture 1, today's lecture, will be focused on four-dimensional guts and constructions of four-dimensional guts. Lecture 2 will describe five-dimensional orbifold gut field theories. And lecture 3 will get us to orbifold gut of the heterotic string. And so you'll see there's an evolution of my thinking in terms of what grand unification is all about. Before I start, however, maybe I should say, why should you be interested in grand unification? And I also should mention that probably this is the most phenomenological series of lectures in this course, and so probably I have to give you some introduction to the notation of the minimal supersymmetric standard model as well. But why should you be interested in grand unified theories? Well, here are some of the virtues of grand unified theories, and by virtues I mean the problems that these grand unified theories solve, problems of the standard model, or problems which they give you a framework for solving. In other words, you can build a solution to certain problems within the context of grand unified theories. So virtues of SUSY guts. First one explains in a natural way why supersymmetry, or the weak scale, is so much smaller than a grand unified scale because of supersymmetry and because that supersymmetry protects the Higgs boson mass and keeps it massless or only gives you logarithmic corrections to the Higgs boson mass until supersymmetry is broken. So if you can explain why supersymmetry is non-perturbatively broken near the weak scale, then you have a natural explanation why the Higgs boson has mass of order the weak scale and not of order the gut scale. In other words, there are no log corrections to scalar masses proportional to the cutoff scale in the theory, or the gut scale. So it explains natural reason why the weak scale is so much smaller than the gut scale. Second reason, it explains charge quantization. Grand unified theories put fermions of one family into irreducible representations of the non-abelian structure of the grand unified theory. In particular, the electromagnetic charge, or hypercharge, has to be embedded in the non-abelian structure of the theory, and because of the non-abelian structure of the theory, the hypercharge is quantized. So charge quantization, but more importantly, we see families, three families of quarks and leptons in the low energy world, and it explains the family structure, particularly if you can put all the families into one or two irreducible representations of the grand unified group. It predicts gauge coupling unification. So by far the biggest hint that there is a low energy supersymmetry, that the LHC might observe supersymmetric particles, is the fact that the gauge coupling seems to unify at a gut scale of order 3 times 10 to the 16 GeV. That does not occur unless you have light supersymmetric particles, which you use in the renormalization group running from the weak scale up to the gut scale. Okay? So the assumption there is gauge coupling unification works, it seems to work, but you have to include those light SUSY particles, which suggests that you should see them at the LHC. It predicts unification of Yukawa couplings. And some of the relations that you get in grand unified theories for Yukawa couplings, which we'll go into in a little bit more detail later, actually fit the low energy data. And so that's a good thing. Now, even with the grand unified theory, it's difficult to make predictions for fermion masses and mixing angles. A typical standard model mass matrix for, say, up quarks is a 3x3 matrix, which is a complex matrix, has 18 parameters in it. There's only 3 up quark masses, and so it's difficult to get out of that 3x3 matrix a prediction. However, if you have an additional structure added on to grand unification, then you can reduce the number of fundamental parameters in the theory and try to get some predictions. And added structure is family symmetries. So if you introduce, in addition to grand unification, symmetries which relate to 3 different families, by grand unification you put families into 1 or 2 irreducible representations. If you now introduce a family symmetry structure, you connect the 3 families, and by symmetry breaking of the family symmetries, you can generate 1, a hierarchy of fermion masses, and 2, you can get predictions because you reduce the number of fundamental parameters in the theory. So family symmetries can give you mass relations or predictions for fermion masses. Sixth reason, neutrino masses. We know that neutrinos have mass and they have mixing angles. Those mixing angles actually are quite different for the neutrinos than for the quarks. For the quarks, the CCAM matrix element, those mixing angles are small. In the neutrino sector, it's known that those mixing angles are large. Nevertheless, you can get predictions for neutrino masses and mixing angles in grand unified theories and get small mixing angles for the quarks and large mixing angles for the neutrinos at the same time. But the interesting fact is that neutrino masses are so much smaller than quark or lepton masses. A border 0.05 electron volts for the heaviest neutrino, if you take a hierarchical neutrino mass relation. And so you would need, if you had standard neutrino Yukawa matrices, you would need a Yukawa coupling for the neutrinos, which is many, many orders of magnitude less than the Yukawa matrix even for the electron, about 10 orders of magnitude smaller, to fit neutrino masses. However, there is a natural way of getting small neutrino masses, and that's the so-called seesaw mechanism. The seesaw mechanism says that the neutrinos, left-handed neutrinos, are coupled to right-handed neutrinos, and those right-handed neutrinos have no standard model charges, and so they can get large mass near the gut scale and generate a small mass for left-handed neutrinos by the seesaw. It turns out that that seesaw mass scale, which fits the data, is around 1 or 2 orders of magnitude smaller than the gut scale. So again, it's another hint for the large scale in nature. If you have R parity in your theory, in your supersymmetric theory, then your lightest supersymmetric particle is absolutely stable. It cannot decay. And therefore, if it's a neutral object, it's a perfect candidate for dark matter. We'd like to explain cosmologically why there are more baryons in the universe than antibaryons, the so-called baryon-antibaryon asymmetry. You can explain that naturally in supersymmetric grand unified theories via a process called leptogenesis. In leptogenesis, and I'm not saying more about this during the lectures, but in leptogenesis you create an asymmetry of lepton number, more leptons than antileptons, and then and you do that maybe at a large scale, about a 10 to the 10 GeV in temperature, Then via normal electroweak processes, baryon number and lepton number are both violated via instanton effects. At high temperature, those instanton effects give you order 1 violations of baryon number and lepton number, and therefore it can convert an asymmetry in lepton number into an asymmetry in baryon number as well. And that asymmetry in baryon number fits quite well the baryon-antibaryon asymmetry of the universe. In any grand unified theory, any theory where you unify quarks and leptons, you can prove, and very nice paper by Gelmond and Slansky, it was proven that protons and neutrons must decay. They're not stable particles. And so you predict proton decay or nucleon decay. And of course, there are experiments looking for this for the last 20-odd years, and they haven't seen a single proton decay. And so there are stringent limits on lifetime of the proton and lifetime of the neutron. And when I say the lifetime of the neutron, presumably everybody knows that a free neutron decays in around 1,000 seconds. However, that's in a baryon-conserving way via weak interactions. However, if you have a proton decay or neutron decay via baryon number violating interactions, a neutron which is inside the nucleus can decay into, say, K0 antineutrino in a baryon number violating way, which would disrupt that nucleus. And you look for that as well at super Kamiokande, and other places look for nucleon decay. So there are limits on proton and neutron lifetimes, which you have to eventually, we hope you'd see, but you have to constrain your theories and discuss whether you should see them already. In any supersymmetric grand unified theory, you might expect, it all works, if there is nothing, no new physics. Once you see the supersymmetric particles, these new supersymmetric particles at the LHC, at the weak scale, then you expect that there's no new physics until you get to the grand unification scale. And so there's a so-called SUSY desert. Now the SUSY desert is very nice in the following sense, because it gives you a huge lever arm at making discoveries near the gut scale or near the Planck scale. By observing physics at the LHC, if there is a SUSY desert, then that observation will tell you something of what's going on at the gut scale or at the Planck scale. And so that's a huge lever arm for experimental physicists, because it would be difficult to build an accelerator to directly prove the gut scale. And finally, I should say that SUSY guts, which we'll hopefully see, are a natural extension of the standard model. Okay? So supersymmetric grand unified theories, if you're going to try to understand what's missing in the standard model without causing much or introducing that much new physics, you introduce supersymmetry, then supersymmetric guts is a natural extension of the minimal supersymmetric standard model, and don't have to introduce anything else except the gut scale physics. Okay, so it's a natural extension of the standard model. Okay, so hopefully that motivates you to want to learn more about supersymmetric grand unified theories. And that's what I hope to do in these lectures. Now, I didn't know where to start when preparing these lectures, and I knew I couldn't start with the standard model. and I couldn't start with the MSSM in order to explain all the notation, et cetera. It would take me 3 lectures. And so we're going to start assuming that you know quite a bit, and I'll tell you where I'm going to start. So here, we'll introduce the standard model very quickly. The standard model is defined by its gauge interactions and the particle content. Okay? It's an amazing feature of known physics that all interactions can be thought of as being local due to local symmetries. The SU3, SU2 cross U1 symmetries are local symmetries. General relativity can be thought of as local Poincare invariance. So all the symmetries, all the interactions we've observed in nature are due to local symmetries, and the interactions of particles, the local symmetries give you gauge particles, gravitons for Poincare invariance, and if you know the charges of the standard model particles, the matter particles under these local symmetries, you know their total interactions with these gauge particles. And so that's what I'm going to give you. So the gauge group, forget about gravity. U1 hypercharge. The generators of the gauge group, I'll use a script T, A equals 1 to 8 for SU3. And of course, really all you need to know at this moment is their commutation relations. And so there are a set of structure constants which are well defined, which define the group. We have SU2 with generators capital T, small a goes from 1, little a goes from 1 to 3. And I'll think of these as operators acting on the particle fields, okay? And they have quantum numbers associated with the charges of the particles under these symmetries. And in addition, we have the hypercharge charge operator. Okay. We have gauge kinetic terms, which I'm not going to write down at the moment. And now we have the matter. In the standard model, the matter, except for the Higgs, are all fermions. And they come in these multiplets. And here, hopefully, this chalk is like butter. We have a quark doublet. The notation. I'm using every field that I write down. These are fields, not just states. Every field that I write down is a left-handed Weyl spinor. Okay, so the notation here is degrees of freedom in terms of left-handed Weyl spinors. We have the leptonic doublet. We have a left-handed anti-electron, and then we have a left-handed anti-neutrino, sometimes called, if I conjugate this, sometimes called a right-handed neutrino. And I will write down their quantum numbers, how they transform. So how tall do you have to be to use all 3 of these? I won't write down everything because there's just too much to write down, but let me just get you started. Under SU3, we have the Gelman lambda matrices, which define the representation, the triplet representation of SU3. And these quarks, the quark doublet transforms as a triplet under SU3. Whereas the left-handed antiquarks transform in the conjugate representation. or 3 bar under SU3. Similarly for the DC, if I ask how the leptons transform under SU3, they are color singlets, and so TA acting on the leptons gives you 0. What about SU2? SU2 quantum numbers, this is small tau, or the polysigma matrices. 2 by 2 matrices acting on Q is the representation that the doublets are in. However, singlets, all the singlets in the theory have eigenvalue 0 under SU2 quantum numbers. And finally, the hypercharge operator. The hypercharge operator acting on, by the way, this defines my normalization of hypercharge. On the quark doublets give you hypercharge a third. On the doublets you get a third hypercharge. On the left-handed anti-electron, the left-handed antineutrino, the left-handed antineutrino has hypercharge 0. The left-handed anti-electron has hypercharge 2. The left-handed anti-down quarks have hypercharge 2/3, and the lepton doublet has hypercharge -1. So those are the quantum numbers under the operation of hypercharge. Now, if you want to know how the quarks and leptons couple to the gauge sector, we just have to write down the covariant derivative, because all the information is in the covariant derivative telling you how quarks and leptons couple. Oh, by the way, with my definition of hypercharge, electric charge is given by T3 plus y/2. So you can evaluate the electric charge of all of these particles using this formula. The covariant derivative tells you how you couple the quarks and leptons couple to the gauge sector. That's the piece of the covariant derivative proportional to the gluon fields, the operator tau A, capital TA, G strong, the strong coupling constant. The coupling to the W triplet under SU2, proportional to the coupling constant G, which is the SU2 coupling constant. And then the U1 gauge coupling, the U1 gauge the gauge field itself be mu. And then we can write down the Lagrangian, which couples the gauge bosons to the fermions and also the gauge sector very simply. It's equal to, you take the Hermitian conjugate of L, the leptonic doublet, and I'll just write it down for the leptons, hopefully it becomes sigma mu bar. It's a 4-component generalization of polymatrices, 2 by 2 matrices. One is the 2 by 2 identity matrix. Plug that in here, and I left out something clearly. And that tells you how the lepton doublet couples to the gauge bosons. And it's a simple exercise just to write down the same thing for all the other states. Okay, so we have all of these states, Q's, UC, DC, L, EC, and NUC. The dots here just represent putting in the covariant derivative sandwiched between the other states like UC star, UC on the right, using the appropriate representation matrices for those states. Plus the gauge kinetic term for the field strengths. This is for SU3. And let me just be a little bit more explicit there. Typically, you define a 3 by 3 for the gluon field. You define a 3 by 3 matrix of gluon fields where G mu A is summed over, and T is the 3 by 3 matrix representation in the fundamental representation. So it's just lambda A over 2. That defines what I mean by G mu, and G mu nu then is a 3 by 3 matrix, which is equal to so that's the gauge field strength for the gluons. You plug it into there, take the trace, and use the fact that I will always normalize my matrices in the fundamental representation to satisfy that relation. Okay, that's the lightning introduction to the part of the standard model which does not contain the masses. Okay, but it's a nice exercise, and I didn't give it as a problem, to take this Lagrangian, the full Lagrangian, and work it out for couplings of quarks and leptons to gluons, W plus, W minus, Z bosons, and photons, and get all the structure that you expect to get by looking at the particle data book, coming out of this simple Lagrangian. However, in the particle data book, it looks a little bit more complicated for the following reason, is that they work in terms of, instead of in terms of Weyl spinners, they work with Dirac spinners. And so let me just tell you the translation that you have to make to rewrite all of this in terms of Dirac notation. For example, a Dirac 4-component electron field is given in terms of 2-component Weyl spinners. And in order to make a 4-component Dirac electron field, you need 2 left-handed Weyl spinners for 1 4-component Dirac spinner. And in fact, those fields are up there. In a chiral basis, for the gamma matrices, this is the 4-component Dirac field in terms of E and EC, these 2 left-handed Weyl spinners. And again, an exercise which is pre-Susie Guts, and so there's no time to go through that here, is to show that if I have a left-handed Weyl spinner and I take the conjugate of it and multiply by I sigma 2, I get a right-handed Weyl spinner. Okay? And so the upper components are the left-handed components of the Dirac electron, and the lower 2 components are the right-handed components of the Dirac electron, all written in terms of Weyl notation. Clear? Okay, what about mass? In order to get mass for quarks and leptons, or for the W and Z for that matter, we have to introduce Higgses into the theory. Okay, so we have to introduce our first scalar. And I'm not going to write down the minimal standard model, which only has 1 Higgs doublet. I will write down the non-minimal 2 Higgs doublet standard model, because that's the one that generalizes to supersymmetric theories. So I'll introduce two Higgs doublets. One I call Higgs up and the other one I call Higgs down. And the upper index is the electric charge of these states. Again, you can write down the interaction of the Higgses with the gluons, Ws, photons, Z's, etc., by just writing down their eigenvalues under SU3. There's singlets under SU3. They are both doublets under SU2. And they have equal and opposite hypercharge, +1 for H up and -1 for H down. In the literature, you'll sometimes see in the discussion of the MSSM, instead of H up and H down, you'll see H1 and H2. I just don't use that notation because I never know which couples the up quarks and which couples the down quarks. Is it 2 or 1? So this makes it a little bit more explicit. Okay, once we have the Higgses, we can now couple the Higgses to quarks and leptons in a renormalizable way. And once the Higgses get a vacuum expectation value, so the Lagrangian, the Yukawa Lagrangian coupling the Higgses to fermions is of the following form. The I and J indices on these 3x3 complex matrices, these Yukawa matrices, are flavor indices, so they go from 1 to 3. Okay, so in addition to an electron, down quark, and up quark 3x3 complex matrix, each one having 18 parameters, we have a 3x3 complex matrix coupling the left-handed neutrinos to the right-handed neutrinos. However, since these guys, these right-handed neutrinos, or these new C states, have 0 charge under SU3, 0 charge under SU2, and 0 hypercharge, we can add a mass term, an arbitrary mass term for these right-handed neutrinos. By the way, I should say that the Lagrangian is this, plus the Hermitian conjugate of this. This mass term, by the way, let me define the notation a little bit more. When I write a little bracket here, and I probably won't do this very often, when I write a little bracket here, that means I'm taking the spinor indices on these two left-handed Weyl spinors and contracting them in a particular way. So this is a two-component Weyl spinor. This is a 2x2 matrix, which is an antisymmetric matrix, index -1 and +1 on the off-diagonal. And this combination makes a Lorentz scalar. And sometimes using other notation, and I don't want to get into dotted and undotted notation, this is simple enough. If I antisymmetrize the spinor indices on these two component Weyl spinors, I get a Lorentz scalar. Not just a rotational scalar, but a Lorentz scalar. Okay? And so this corresponds to a mass term. It corresponds to what's called in the literature a Majorana mass term for neutrinos. Why is it a Majorana mass term? Well, because it doesn't preserve any symmetry. The only possible symmetry is when we discuss the theory in terms of Weyl spinors, we can make phase rotations of all the fields. Typically, that's a symmetry. For example, it's certainly a symmetry, a phase rotation of the lepton doublet is a symmetry of the kinetic term. A phase rotation of the lepton mass term would be a symmetry if I take L rotated by one phase and EC rotated by the opposite phase, I get a symmetry. That symmetry could be called fermion number, or it can be called U1 electromagnetism, depends on how it couples the gauge fields or whether it couples or not. But that's a symmetry of these Dirac terms. However, since I have nu C here, there's no way of writing down a symmetry in general with an arbitrary M. There's no way of writing a phase symmetry. So the phase symmetry, so-called chiral symmetry, is broken by this Majorana mass term. And in fact, that's the key ingredient of a Majorana mass term. It breaks fermion number by 2 units. Okay? So we have a Majorana mass term for right-handed neutrinos, and when we integrate that out, we'll generate left-handed neutrino mass matrices. Okay? And I'll come back to that later. The Higgses couple again with the covariant derivative to gluons, W's, and B gauge boson. So you write down the Lagrangian for the Higgs as well. In addition to that Lagrangian, the kinetic term for the Higgses coupling to gluons, W's, doesn't couple with gluons, but W's, and B, the Higgses have a potential which you use to drive a vacuum expectation value for the Higgs field. Of course, this part of the theory has not been well established by observation, and we're still looking for this Higgs, the massive Higgs boson, physical Higgs boson that results. However, we'll assume here that we have such a potential and that the Higgs gets a vacuum expectation value of the following form. Higgs up gets a vacuum expectation value in the neutral component of the Higgs. And similarly for Higgs down. Where for the moment we'll assume both of these are real. And the ratio of the Higgs up to Higgs down expectation value, write it like this, call this VU. Call this quantity VD. The ratio VU over VD in the literature is called tangent beta. It's an arbitrary parameter which we don't have experimental verification for, and so therefore it remains arbitrary. There's some bounds on it. And V, the sum of the squares of H up squared and H down squared, their expectation value is fixed by the W mass, or by the Fermi constant. And so we know the value of V, it's around 246 GeV. Okay. There are constraints from LEP data which suggest that tangent beta is greater than about 2.4. There is no upper constraint. Well, there are some constraints from I think it's Tevatron data that says that the upper bound on tangent beta, but there's lots of assumptions, is around 60 or 70, roughly speaking. So I don't see the picture in my mind, so that's a rough number I remember. But these are from that data. Assuming supersymmetry, what regions of supersymmetry parameter space can you rule out? Okay, and so you have a range between around 2 and 60, which is acceptable with all data. Answer your question? Okay. Up until now, I haven't said anything actually about supersymmetry, so I have to quickly supersymmetrize all of this. Now, another reason why I'm using the formulas that I'm using is because very easily to supersymmetrize this. So now let's discuss the SUSY standard model. Every one of the fields that I had, Q, UC, DC, lepton doublet, etc., becomes a superfield. Every one of the fermion fields becomes a chiral field n equal to 1 supersymmetry. So for example, the electron field that we had becomes now part of a left-handed chiral field where theta is a two-component Weyl spinor, left-handed Weyl spinor, which satisfies Grassmann algebra. Y is related to space-time. We have the scalar component of the lepton field, or the superpartner of the lepton is the scalar lepton. We have the fermionic doublet E contracted with theta to give you a Lorentz scalar. And we have the auxiliary field for the lepton. Now, I've just done this for the electron, but you can do the same thing for the UC, the DC, the Q, up, U, the D, etc. All the fields now get supersymmetrized, and we have super chiral multiplets, left-handed chiral superfields. This coordinate y is equal to x and that you can find in the literature, so I won't say anything more about that, why you write it that way. But what I have to do now is to very quickly write down the interaction of quarks and squarks and leptons and sleptons with the gauge sector, and then the gauge sector itself in supersymmetry. And again, I apologize. Hopefully you know most of this, and just setting notation. The gauge matter Lagrangian is of the following form. We do an integral d4 theta, which is d2 theta star, over the Grassmann variables. For the leptonic doublet, we have, instead of little l, I, we now have a superfield, capital L, which is a function of theta and y. We take its Hermitian conjugate. We multiply it by exponential minus 2. And now we have a sum of terms. And I'll write down the full sum. There is a superfield, a gauge vector superfield, which contains the gluons and the gluinos, and the auxiliary fields for the gluons and gluinos, which you'll find in notation, say in Diane's lectures that have been posted. GS is the strong coupling constant. It's the same one that we've seen in the standard model. There is a Weno superfield V, which contains the W, the three components of the W gauge bosons, coupling constant G, which is the SU2 gauge coupling constant. These objects are, this is a 3x3 matrix, just like G mu A was G mu was a 3x3 matrix. This is written in terms of components multiplied times TA, the generator in the triplet representation of SU3, to make it a 3x3 matrix. In fact, this is multiplied times tau A, the generator for the SU3 in an arbitrary representation, and then you use the quantum numbers of the states that are on the right-hand side to determine what goes here. Same thing for this. The I index is a flavor index, and you do the same thing for the quark doublets, which are called capital Q now. You do it for UC, for DC, and for EC, and for NC, the supersymmetrized, all the quarks and leptons have been supersymmetrized. And so that's what the dot dot stands for. You write down the same thing. The generators take into account what representations they're in. Okay? Of course, you have to write down the gauge kinetic term, which I'm not going to write down. It'll just be more notation. I'm not going to use it later. I just told you VG here. Etc. And then you have to write down the supersymmetrized version of the Yukawa couplings, which is given in terms of a superpotential. And the superpotential, I'm not going to write it down now because all you have to do is take the formula up there and replace little li by capital Li, little ec by capital EC. HD is supersymmetrized as well. The first component of HD is, so let me just state that HD now supersymmetrized has a first component which I'll call HD. A second component which contains the Higgs fermion. And the auxiliary field. And so you supersymmetrize everything and write that and call it the superpotential with the same Yukawa matrices that we had before. Okay? The only thing I have to add to the superpotential, which is not there, I have to add a term of the following form. So, by the way, in addition, you've added an NIC and an NJC, capital N, capital J. So you have a supersymmetric mass term for your Majorana neutrinos, your right-handed neutrinos. And so the only thing that we have to add new is a mass term for the Higgses, H up, H down mass term. Is it clear? Okay, so very quickly, lightning speed, which was not so lightning, we've introduced the MSSM. So let's get to grand unification. There are at least two roads to grand unification. The road that I will start with is called PiTP-Salam. We have quark doublet and lepton doublet. They both are doublets under SU2. One is a triplet under SU3. The other one is a singlet under SU3. What PiTP-Salam suggested in 1973 is to enlarge SU3 to an SU4 where lepton number is the fourth color. Okay, so we have an SU4 multiplet now, and this is a triplet under SU3 and a singlet under SU3 together. It's a fourplet under SU4. It's a doublet under SU2. So we have an SU2 left. We have an SU4 color. And what to do about the left-handed antiparticles? Well, we're going to combine them in the following way. If we take all of those states, we can make another fourplet under SU4. It's actually a 4-bar under SU4. And it's a doublet under something. In fact, it's a doublet under an SU2 right gauge symmetry. So the representation content here is this is a 4, 2, 1 under SU4 cross SU2 left cross SU2 right. And these states transform as a 4-bar under SU4 color. a singlet under SU2 left. They're left-handed singlets, but they transform as a doublet or a 2-bar under SU2 right. Okay? And so we've unified quarks and leptons into 2 irreducible representations of this SU4 cross SU2 left cross SU2 right Patti-Salam group. And by doing that, it's not a grand unified theory, but by doing that, we've embedded hypercharge into a linear combination of SU4 and T3, or SU2 right. Okay? So we've quantized hypercharge in the process. And so we have charge quantization where electric charge is equal to T3 left plus T3 right plus 1/2 baryon number minus lepton number, because in fact when you break SU4 color down to SU3 color, you get an extra U1. And that extra U1 you can identify as B minus L. So B minus L is coming out of SU4, and by definition B minus L is just equal to, it's a diagonal matrix which commutes with SU3. It's traceless because it's coming out of SU4 and it has those quantum numbers. I've just normalized it arbitrarily so that it is baryon number minus lepton number. This whole thing here is what I called hypercharge divided by 2 in the standard model. And so we've quantized hypercharge by unifying quarks and leptons. We get simple unification relations just from Patti-Salam alone. We get Yukawa unification. We don't get gauge coupling unification, but we do get Yukawa unification. So we can take, let me define Q is equal to this 4-2-1 multiplet under Patti-Salam. Let me define QC is equal to this 4-bar, 1-2-bar multiplet under Patti-Salam. Where are the Higgs? Well, there's in Patti-Salam 2 Higgs doublets that we introduce for supersymmetric purposes, because we need 2 Higgs doublets, appear in one irreducible representation. And the matrix structure is the following. And you work it out, this transforms as a 1-2-2-bar. They're both doublets under SU2 left. SU2 left acts from the left. And they're anti-doublets under SU2 right. HD goes to HU under SU2 right. Okay? And you can use this to calculate the hypercharge of HD and HU. And so we've put the 2 Higgs doublets into one irreducible representation of Patti-Salam, and by doing so, if we wrote down if we only had one family of quarks and leptons and wrote down the most general renormalizable Lagrangian coupling the Higgses to the quarks and leptons, we have one coupling constant. One irreducible interaction coupling the quarks and leptons to the Higgs doublets. And that tells us the following. This has to give you the coupling of the top quark, the bottom quarks, the tau lepton, and the tau neutrino. So we get what's called Yukawa unification. All 4 couplings are equal by symmetry relationship at some scale, which we'll call the gut scale. Now, in the notes, I say that this is not a grand unified theory. Therefore, there are, in fact, even if you have a left-right symmetry, a parity operation, which takes SU2 left to SU2 right, that eliminates one coupling constant, one arbitrary coupling constant, you can still have 2 coupling constants at the large scale, and so therefore there are 2 coupling constants. You don't get gauge coupling unification, and so you can't make any predictions for low energy physics. from the gauge couplings themselves. However, I want to go from this PaDi-Salam now up to a grand unified theory, which actually is very nice because it unifies the gauge couplings as well as putting the quarks and leptons, these two guys, together into one irreducible representation of SO10. So very quickly, SO10 this is SU4 PaDi-Salam. Well, SU4 is homomorphic to SO6 as a group statement. So those two symmetries are related. And in fact, SU2 cross SU2 is homomorphic to SO4. And so PaDi-Salam is equivalent to and it's no stretch of the imagination to realize that this is a subgroup of SO10. And so we get very quickly to SO10 grand unified theories. In SO10, the spinor representation of SO10 contains one family of quarks and leptons. And in fact, if you take SO10 and break it down to PaDi-Salam, you get those states. Okay? So now, if we have a grand unified group, which is SO10, we put the quarks and leptons into one irreducible representation of SO10. It gets, in fact, this symmetry here, this relationship here, gets generalized now to be written like this, because we're going to put the Higgses in the 10-dimensional representation of SO10. In fact, from this analogy, it's very easy to see how the Higgses come out of the 10-dimensional representation, because this is equivalent under SO6 cross SO4. This is equivalent to a 1, 4 under SO4. It transforms as a 4 vector under SO4, the 1, 2, 2 bar under SU2 left cross SU2 right. So that's just the 4 vector component of a 10-dimensional representation. And the other 6 states transform as a 6 vector under SO6. Okay? So the Higgs is part of a 10-dimensional representation of SO10, where these two Higgses of PaDi-Salam transform as a 4-plet under SO4, and the color triplet Higgses that are going to come in transform as a 6-split under the SO6, which contains color. Okay? So the 10 breaks down into the in this net language, it breaks down to a 6, 1, 1, plus a 1, 2, 2 bar. And that's the Higgses. And so we don't get any new relationship for Yukawa couplings. We still have this relationship that there's one universal Yukawa coupling in SO10. But we now have only one gauge coupling, and so we get some prediction for gauge coupling unification. If you're going to do this whole exercise in string theory, you're going to start talking about weight space for your momenta. Your momenta of your string live in weight space, particularly for the heterotic string. And so let me just write down the weights of S for the weights in Cartan Weil basis for SO10. The roots of SO10, the gauge sector, it's a 5-dimensional weight space because it's a rank 5 group. SO10 is a rank 5 group. The roots are plus or minus 1, plus or minus 1. These are the non-zero roots of SO10, where you have to permute all the permutations of where you put the pluses and the minuses. The 10-dimensional representation is simply given by this, where again you take all possible places for putting the plus or minus 1. That gives you the weights of the 10-dimensional representation of SO10. And finally, the spinor representation of SO10 is represented by plus or minus a half with 5 plus or minus 1/2 spinors. And for the 16, we have to have an even number of minus signs. And the 16 bar will have an odd number of minus signs. And of course, that's arbitrary whether you define it as, which you define as a 16 or 16 bar question.
It does the breaking to Fatih-Salam, and then it does the left-right, the SU2, right?
Oh, no, no. If we want to talk about gut breaking, I'll come back to that, but let me answer your question directly. In order to do gut breaking, typically in SO10, first of all, in order to preserve gauge coupling unification, we wanted to either go through SU5 or break directly down to the standard model at one scale. In order to get to SU5, we need a 16 and a 16 bar getting vacuum expectation values in the right-handed neutrino direction, because the right-handed neutrino is an SU5 singlet. Okay? So if that gets a vacuum expectation value, a scalar component of a right-handed neutrino superfield gets a vacuum expectation value, it breaks SO10 down to SU5. And then we need an adjoint representation of SO10 to break down SO10 directly to the standard model. So we need adjoints in 16 and 16 bars, the simplest thing to do it. Not the 10. Okay. Up here, I have the one family of quarks and leptons in terms of their weights in SO10. Okay? So what we have here is states with an even number of minus signs. The plus or minus means plus or minus a half. These three indices can be thought of as color indices. The SU3 color is embedded, raising. By the way, what does SU5 do? These are the roots. These are the objects which move you around in weight space, right? And so you have roots which raise two indices and lower two indices. Those are purely SO10 roots. Or you have roots which raise an index and lower an index. A root which raises an index and lowers an index is actually a subgroup, is actually SU5 subgroup of SO10. So if you want to know what the SU5 subgroup of SO10 is, in Cartan-Weil notation, the SU5 subgroup is a 5-index object. The weight space is, and you raise and lower one index. So if we want to figure out what are the SU5 multiplets here, if we raise and lower an index, that's all we're allowed to do. By the way, if you have plus a half, you cannot get higher than plus a half. So raising a plus a half gives you 0. You can't get lower than minus a half, so lowering a minus a half gives you 0. Okay? So those are the limits. So this nu C up there, you can't raise any index there. And so what you can do, the only thing you can do using SU5 roots, you get 0, because SU5 has to raise and lower one index. So acting on nu C, you get 0. And nu C is an SU5 singlet. However, using an SO10 root, which allows you to raise two indices and or lower two indices, you can go from nu C to EC. And in fact, that's the right-handed doublet. Raising two weak indices or lowering two weak indices take you from nu C to EC, and you can identify the SU2 right embedded into SO10. It goes from nu C to EC. If you look at these states, the states with two minus signs, if you're in the space of states with two minus signs, you cannot get out of that space of states with an SU5 operation, which raises and lowers an index. It doesn't change the number of minus signs. And so therefore, all the states with two minus signs, which includes EC, the quark doublets, and DC, and UC here, all of these states between here and here, there are 10 of them, are the 10-dimensional representation of SU5. So SO10 breaks down to a singlet, the 16 breaks down to a singlet, a 10-plet, and a 5 bar, all of these states have 4 minus signs, and so you remain in those space of states with an SU5 rotation. Okay? Okay. I'm going very slow, unfortunately. That was the advantage of giving a Blackboard talk. The disadvantage is I don't cover what I want to cover. Okay, want to discuss SU5 very quickly. Discuss SU5 because I want to discuss gauge coupling unification. The group SU5 is defined by the set of 5 by 5 complex matrices U, which satisfy determinant of U equals 1, and U dagger U is equal to 1. So these are 5 by 5 complex matrices. Under multiplication, this is a group, and this defines the group SU5. A 5-plit under the group SU5, I'll define it with an index up. It transforms in the following way. So 5 means a 5-plit of SU5. It means a field, a Weil spinner, which we're going to have 10s and 5 bars to form the standard model states. That's how it transforms under an SU5 rotation, where U can be written as exponential of I, TA, and a parameter, real parameter WA. And TA are the traceless Hermitian matrices, 5 by 5 matrices, which are the SU5 generators in the 5-dimensional representation. And if you expand this out, you can define the rotation of the 5-plit under a linear SU5 transformation. So this is how it transforms linearly under this SU5 rotation. And what I want to do quickly is identify the SU3 cross SU2 cross U1 subgroup of SU5. And I'm going to do this very quickly because you probably have all seen this, and it's explicitly in the notes. So the SU3 subgroup of SU5 of these generators is written like this in the 5-dimensional representation. A goes from 1 to 8. Those are the SU3 generators, 3 by 3 matrices. The SU2 subgroup of SU5 let me write it like this. Tau 2 by 2 polymatrix A minus 20 for A equals 21, 22, and 23. Those give you the SU2 generators of SU5. Clearly, these commute with these. There's a U1 generator, which is hypercharged, which we'll work out in a second. And then there are all the other generators, which are not in SU standard model, which are in SU5 divided by the standard model gauge group. And those generators, TA in SU5 over SU3 cross SU2 cross U1 have the following form. A runs from 9 to 20, so there are 12 of them. And again, in block diagonal form, they look like this. Essentially, what they are polymatrices just in a different space. And so take these and put the 1 or the i's in all the 6 spots, and you get all the matrices of SU5 over SU3 cross SU2 cross U1. And they satisfy, with the addition of a U1 matrix which commutes with these, give you the SU5 generators on the 5-plit. And the last generator contains hypercharge, and this quantity here is just what I called hypercharge divided by 2, acting on a 5-plate. So I'm going to skip quickly and just tell you the following. I'm going to give you the result that a 5 contains the following states: a D colored triplet and a leptonic doublet, but they're not the right states. If you work out the quantum numbers using the formulas that I have here, this doublet D, this color triplet D is a triplet and it has hypercharge minus 2/3, and the leptonic doublet that sits there has hypercharge plus 1. So it has the wrong quantum numbers for the standard model states, the leptonic doublet. And that suggests looking at the states in a 5-bar. The states in a 5-bar are the conjugates of these. And these are the things we'll call DC with index A and LCI. I goes from 4 and 5 as an SU2 weak index. A goes from 1 to 3. It's an SU3 color index. And that quantity, those quantities, DC, is a 3-bar, a 1 and plus 2/3 under hypercharge. Of course, it's the conjugate state. And the LC, let's write it out. First of all, it's a 1, a 2-bar, and a minus 1 under hypercharge. It has the right quantum numbers to be a leptonic doublet. And if you write it out, it contains these states. Minus the electron field upper and the neutrino lower, because it's an anti-doublet. And you can use now the standard T3 plus Y/2 to calculate the electric charge of this or this. Okay? Okay, so that's what appears in the 5-bar. We've identified this hypercharge, and we've identified the states of a 5-bar. We've identified everything. Now, where are the other states of the SU5 or the 1 family? And in fact, what you have to do is show self-consistently that they appear in a 10-dimensional representation. And so, again, as part of your assignment, you can think of trying to show that the 10, which is an antisymmetric, 2-index antisymmetric tensor under SU5, calculate its transformation properties under SU5, its infinitesimal transformation properties under SU5, and show So that's the states that appear in the 10-dimensional representation, and their charge assignments under SU3, SU2, and hypercharge is already defined, and you can prove that those are the right quantum numbers for those states. Okay. In this theory, we have in SU5 or SO10, we will have 1 gauge coupling at a grand unification scale. And we have 2 parameters. We don't know what the grand unification scale is a priori, and we don't know what the gauge coupling is at the grand unification scale. So in our fundamental theory, we have a parameter we'll call alpha gut and a mass parameter m gut. We don't know what those 2 parameters are. However, at low energies, we have 3 gauge couplings, alpha 1, alpha 2, and alpha 3. And so we can use 2 of those low energy gauge coupling constants to figure out what alpha gut and m gut are. And once we know what that value is, we can then run down and make a prediction, say, for alpha 3. Okay, and that's what is now done. So the Lagrangian that we start out with, let me just be explicit, the Lagrangian that we have for fermions is equal to 5 bar alpha dagger sigma bar mu. There's an I here. covariant derivative d mu alpha beta times 5 bar beta. Covariant derivative d mu, as everything else, defines all the gauge interactions. There are the 24 gauge bosons of SU5, the generators of SU5 in a particular representation. You have to put it in, say, in this case, it's the 5 bar representation, not the 5, which is what I gave you before, plus these are all Weyl spinners. And now you have the complete coupling of all the SU5 generators to the 5 bar and the 10, which is one family of quarks and leptons. And from this, and since we have one gauge coupling constant here, we get a boundary condition at the gut scale which says that G3 is equal to G2, the SU3 coupling, the SU2 coupling. A U1 coupling is all equal to the gut coupling constant at the gut scale, okay? And now the question is, what's the relationship between G3, G2, and G1 to the low energy couplings that I defined earlier, G prime, G, and G strong? And it's easy to show, well, first of all, we choose the same normalization for our generators in the fundamental representation as we have before. And so the SU3 are normalized and the SU2 are normalized as before. And so we find out that G3 is essentially G strong after we take into account threshold corrections at the weak scale. G2 is essentially G, the SU2 gauge coupling constant, after we take into account threshold corrections at the weak scale. And G1 is equal to root 5/3 G prime, okay? Because T24 and hypercharge have an extra factor of root 3/5 between them. And so remember, the B mu couples to Y over 2 times G prime. And you just have to rewrite that in terms of G1. Okay, and you get this simple relation. Okay, so these are the boundary conditions that you would have at the gut scale without any threshold corrections, and you can use these to make predictions. So quickly, what kind of predictions do we have in the last? It's true I got less than 10 minutes, right? Unfortunately. Okay. At one loop, you calculate renormalization group equations from the gut scale down to the weak scale. You get the relationship that alpha I goes from 1 to 3, the 3 gauge couplings, at inverse at mz is equal to alpha gut inverse minus bi over 2 pi log m gut over mz. This is a one loop relationship, assuming no threshold corrections at the weak scale, no threshold corrections at the gut scale, and just one loop running, which is self-consistent. But what people do nowadays is use 2 loop renormalization group running from the weak scale to the gut scale. They include one loop threshold corrections, including SUSY particles being integrated out at the weak scale, and possibility of threshold corrections at the gut scale. The coefficient B for the MSSM is equal to minus 33 fifths, minus 1, and 3. And so you just use those simple renormalization group equations, and you use the following relationships. What's the relationship between alpha 1 and alpha 2 at the weak scale and alpha electromagnetic and so-called sine squared theta W? Well, Okay, so their alpha electromagnetic evaluated at the weak scale has a value of about 1 over 128. It's not the same value as it is when you evaluate it at the electron mass, which is about 1 over 137. So you renormalize up to the weak scale. Sine squared theta W is a linear combination this linear combination of G prime and G, and you work this out. This is just pure standard model physics. So precision electroweak data gives you the value of alpha electromagnetic NMZ. Roughly speaking, it's around 1 over 128. And sine squared theta, roughly speaking, is around 0.23. So, if you plug that into the renormalization group equations, you can take, for example, the difference of alpha 1 minus alpha 2. That will cancel out the alpha gut. You just get a function of m gut over mz. Taking the difference, measuring alpha 1 and alpha 2 at low energies, and taking that difference, you predict what m gut is. Then taking alpha 2 at mz, using renormalization group equations, once you know what m gut is, knowing what alpha 2 is at mz, you get the gut scale, alpha gut. So just say it again. Alpha 1 and alpha 2 at mz. By the way, in the notes, all of this is worked out in detail, so I'm just not going to work it out here. You get alpha gut and m gut. Okay? If you use, and in the notes, I work it out in detail for both the standard model without supersymmetry and with the supersymmetric, minimal supersymmetric standard model. Once you have alpha gut and m gut, their values are different depending on whether it's supersymmetric or not. If it's not supersymmetric, m gut is of order 10 to the 13 GeV. Alpha gut is like 1 over 40. If it is supersymmetric, m gut is around 3 times 10 to the 16 GeV. It's much larger. And alpha gut is like 1 over 24, okay? It's in the notes. Once you have alpha gut and m gut, you use the equation here for alpha 3 to figure out what alpha 3 at mz is. It's a prediction, okay? You know what alpha gut and m gut are, you predict alpha 3 at mz. If you don't use supersymmetry, if you know supersymmetry, you get alpha 3 at mz is around 0.07. The experimental value for alpha 3 at mz is like 0.1 or 0.12 roughly. The exact number is in the notes. So this is almost a factor of 2 wrong, not using supersymmetry. If you use supersymmetry, you find out alpha 3 at 1 loop, mz is around 0.12, which is almost right on, fitting the low energy data. And I don't have time to go into what we'll start next time, is to show you that once you include 2 loop running from the weak scale to the gut scale, and you include 1 loop threshold corrections at the weak scale, this beautiful 1 loop prediction actually goes a little awry. And you need some threshold corrections at the gut scale to fit the low energy data. But they're not large, around 3-4%. And in fact, what you can say in the other way around is that any realistic gut will have threshold corrections at the gut scale of order a few percent. And by measuring precisely the low energy value of alpha 1, alpha 2, and alpha 3, you're measuring some properties of the physics at the gut scale, as I said, in the Suzy Desert. So at the moment, I don't think it pays to go any further.